So we're now recorded in no less than 3 different places. And okay, apologized for the generating of 2 Gradescope pages. Put your homeworks in any one of them, and we will figure out how to move it to the correct one. I can tell you all the technical details of why it happens, but let's. It would be boring. Yes, absolutely. Go ahead.
Just like for clarification, homework zero's due date got pushed back correctly?
Yeah, yeah.
I just wanted to make sure.
And I said that, and you'll get the and the grade that you need to get on it is more than 50%, and it only counts for 1 point from the. So it's no more than checking that the whole process of you the generic queue, read it from the overleaf, and I suggest again read it from the overleaf, not from the PDF, just in case there are any comments that you can see it in online. Read it from the overleaf, write it in a way that we can read and upload to Gradescope, that all of it goes smoothly. There is no and to mention to you a few items that I don't want to spend too much time in this course because you're supposedly knowing it from previous courses. I can go make a quick review if people would ask them specifically, but otherwise I'll go through them quite quickly. Any other questions? I can barely hear you. Can you repeat? Was it Max?
Oh, my bad. My mic I was unmuted and I just joined. Sorry.
Sorry. There was a question.
I think he was saying it wasn't a question, it was just background noise.
Superb. Good. We talked about what is omega of some function. When can we say that a function is order of n or order of n squared? Any other questions about the homeworks? Anything about the course? Bureaucracy? Okay, fantastic. Yeah, we talked about what is big O, what is big omega. Let's go over it. Omega is not nearly as important in this course as O, but and you'll see we will mention it a few times in the course, but it's not nearly as frequently as big O. So I have some algorithm whose running time is T of n, and I can say that it's omega of, say, n, omega of n squared, omega of 3 to the n, omega of something, I'll call it g of n, n is the size of the input as usual, say the size of the array, if and only if, we'll use this abbreviation a lot, if and only if there exist positive constants C2 and N0 such that the running time T of n is at least as big as G of n, is at least n cube, is at least n square, is whatever I want to do it, as long as n is large enough. As usual, I don't care about small n's. All the algorithms runs really fast. If the input is minusculous, only large inputs I care for. So only if n is larger than n0. I mean, it could be also if n is smaller, but then you're not legally obliged to be correct for small n. To have this claim, P of n is omega of n squared, to have this claim correct, it's enough that it's true only for some large threshold of large input of n0. And what is this mysterious constant C1 over here? It just tells me how do you count the time. Are you counting the time by weeks of CPU? Are you counting it by seconds, microsecond, elementary options? Are you implementing it in C or in Python? Python is slower than C, will be larger, but it doesn't affect the basic behavior of the algorithm, what we call the asymptotic behavior when n is becoming larger and larger. We want to show what the shape of the graph, not what are exactly the constant. So as long as you can claim that there are such constants C1 and N0, you don't, usually I don't need to show what are these constants. Okay, then we can say that the running time is omega of g of n. And maybe it's true, maybe it's not true, depending on what is g of n and depending what is the running time t of n that we are talking about. Why do we like so much big O and big omega? There are several reasons. One of them is that it allows us to get rid of noise. We have I have ADHD. I want to concentrate on the little thing, on a few things that highlight the big behavior of the algorithm. So if there is an algorithm whose running time is, I first execute one function whose running time is 3n cubed. When this is done, I execute another function whose running time is 90n squared, minus a little bit, plus some constant. This constant comes because maybe I need to upload to the memory all the data and push things to the stack. I can never say if this is good running time or bad running time. However, this is omega of n cubed. So I can now compare algorithm with omega of n cubed compared to omega of n squared. And remember, it means when I'm saying omega, I mean the algorithm doesn't always need to run in omega of n squared, but there is at least one bad input that will cause the algorithm to run in this time. So let's think about it. Big O said the algorithm never takes more than n squared. Big omega said there are bad inputs that will cause the algorithm to run in at least n squared. There is a more detailed slide coming up. Okay, what is theta notation, big theta? So we say that t of n, running time on an input of size n, is theta of, say, n squared, or theta of n log n, or theta of whatever you want to write here, if and only if, let's make it first formal so nobody can understand, if and only if you can generate three constants, C1, C2 of n0, such that for every n that is at least larger than n0, only then you have legal responsibility, only for large n. T of n is no larger than some constant times g of n, and no less than another constant times g of n. Oh, I have a typo here. This C1 should be C2. Please correct. This C1 should be C2. That is, it's not the same constant that you're talking about, but t of n is somewhere sandwiched between these two functions. Or, in other words, we can say that t of n is theta of g of n if and only if, at the very same time, t of n is order of g of n, and also t of n is omega of g of n. Both are true. It's completely obscured without an example. So let's think about an array of size n. What is the size of the array? The array is becoming larger and larger. I think about it as a processing time where the inputs, it's big data question. My input is going to be larger and larger and larger, and I want to ask what the running time of the sorting algorithm as n is becoming larger and larger. And if we think about algorithms like bubble sort or insertion sort or swap sort, none of them will ever take more than n squared. A constant time n squared. Like most, if you think about insertion sort, you're checking every I and j and maybe swap between them. For every I and j in the range of the input, you're looking at if if the key at index I is smaller or larger than the key at index j, and maybe swap between them. So you're checking about n square many values. So all these algorithms run in order of n square. Maybe not all of you know the whole three: bubble sort, insertion sort, and swap sort. You need to know at least one of these threes, hopefully insertion sorts. And so, however, I'll use them as an example. The running time of all of them is order of n square. It's not more than a constant. You remember, and the rule about a constant, you tell me what is this constant. You can pick whichever constant you want, as long as it's not zero, of course. But once you told me what is this constant, how do you measure time? You decided to measure the time in weeks, that's fine. But once you set out your mind about the constant, you cannot change your mind. You cannot say that if n is becoming larger, then the constant is becoming larger. Then it stopped being a constant. It's becoming a function. Once you told me how do you measure the units of time, you cannot change your mind, and that's a constant that you're talking about.
Yeah, but
I'm sorry? So all the algorithms are order of n square, but I don't have the chat with me. Yeah. Just want to have also the chat. Okay, so all these algorithms takes a order of n square. I don't have the chat at the moment. If somebody wants to ask, just speak. Order of n square. On the other hand, each one of these three algorithms, and for every n that you have in mind, I can always generate an input to these algorithms such that the running time will be no less than n square. And a common example would be if the array is sorted in a decreasing order, array is sorted downward, and now I want to sort it upward. Usually that's the worst input to all these algorithms. So the algorithm, there is some input that causes the algorithm to run in at least omega of n square. So if it's omega of n square, no less than n square, and no more than n square, then I can say that the running time is theta of n square. Okay, that's the meaning, not more and not less. It's sandwiched between the n square, maybe with different constants from both sides. So that's omega. Just a few quick examples, just to make sure everybody remembers. If t of n is order of n square, that's a legal statement. Maybe it's true, maybe it's not. T of n, as usual, the running time on an input of size n is becoming larger and larger. Maybe I say, and I'm correct, T of n is order of n square for one particular algorithm. If this is true, then think why. It's obviously also true that T of n is order of n cube. Right? I don't necessarily tell you what is the tightest, what's the lowest lower bound. I just have to tell you one lower bound, so T of n is also order of n to the power to cube, because this is larger than this. If this is true, then this is true as well. T of n is also order of n to the 3.5. T of n is also order of 2 to the n. All these three statements are true if this statement T of n is order of n square is true. Think about the O as a macro, an alias into much larger, much longer sentence that says, oh, I can show you these two constant and 0, C1, such that for every n larger than n0, something is satisfied. So if this claim is true, then all these three claims is true. Now, is this also true that T of n is order of n to the 1.5, less than 2? Maybe yes, maybe no. I don't know by itself. However, if you tell me that in addition to this running time, T of n is omega of n squared, meaning you can find an input that the algorithm runs in no less than n squared, then it is impossible that T of n is order of n to the 1.5. These two statements contradict each other. Okay. So, and what is the practical importance for you in your market, in your future life? Why is it so important for you to know about big omega? Well, you need it to keep your job. Your boss tells you your piece of the code runs way too slow and you are slowing down the whole project. Do make your code faster or else. And then you are coming back to your boss and says, well, actually, what the problem that you asked me to solve is omega of n cube. It's known that there is no algorithm that runs in better than n cube to the problems that you ask me to solve, and I already generated an algorithm that runs in order of n cube. Again, you will say that the problem is omega of n cube, meaning we can show, I'll use a different marker. You'll say, people have proven that the problems that you ask me to solve cannot be solved in time better than n cube, and my algorithm already runs in order of n cube, and this is known, meaning that you might still improve the constant. Maybe that's still your job might be on the line as far as improving the constant, but as far as the high order bit, you can now have a proof that your algorithm is optimal. If it's known that no algorithm runs in better than n cube, and your code runs already in n cube, then of course you cannot get any algorithm that runs faster than this, if this is true. And there are problems that it's known that there are no better bound. For example, no better bound for some problems than n squared. Other problems, it's known that it's not, meaning that the big O is not only about a specific algorithm, but the big omega refers to the whole problem as a whole. You can prove, or one can prove, or one had proved that there are no algorithms that will solve them in time better than omega of something. For example, that's the most famous one. If you're talking about sorting of n keys, and these keys can be anything like float numbers, can be floats in any range, then any algorithm that will sort n values runs in at least n log n. It's a theorem. Any algorithm that sorts n float keys runs in omega of n log n. Okay, so that I'll have to, that sorts n keys runs in omega of n log n. We cannot beat it. So how come how come a radix sort runs in linear time? By the way, how many of you knows radix sort? Did you cover it in 345 or elsewhere? Can you show me hands if you have studied radix sort? 1, 2, 3. Okay. Okay, perfect. Yeah, you know your way, radix. Sorry?
Sorry, I was just going to say we touched on it in 345, but we didn't study it extensively.
Okay, maybe if I have time, I'll go over it. It's beautiful, brilliant algorithm and extremely useful. It's yeah, I'll try to get to it. I'll try to make time to get to it. Um, it's doing a few things that are so counterintuitive and so much not something you'll expect to work that I find it really cool and very useful. Anyhow, how come radix sort can sort n keys in linear time? Linear is less than omega of n log n because your keys are not floats. Your keys are in much smaller range. They need to be integers. They cannot have too many digits. There are a lot of constraints about the type of the input. If your keys are anything else, then you need at least these many you need at least n log n many comparisons operation. Comparison operation, I'm looking at a key AI, I'm looking at a key AJ, and I need to ask if AI is larger than AJ, then I'll do one thing, or I'll do another thing. And you can prove that you can know if you didn't execute at least these many comparison operations, then your output cannot be really sorted. I'll show you two outputs that are not in the same order, but you cannot say if one or the other. So in this sense, sorting is it worth knowing. You cannot sort in time better than n log n unless your input is very, very friendly. Okay. And just to make sure, this course is not about recursion formulas. This course is not about big O. This course is not about theta. It's only the language that we are trying to generate so we can get to the cool things, which are the algorithms. Yeah. So doesn't mean that I will not ask questions about it, but if you're losing me now or you just feel that that's not what you want to do in life of massaging big O of things, that's not what this course is about, and we are going to move to different cooler things very soon. Nevertheless, here are a few examples that I generated, not from any textbook, sorry, but I think that they are explained in the slides quite well. And I mentioned to you there is already one course of mine from previous years that you can find on Pinapto. And if you'd like, I explained it many times. I have several recordings if you don't find it in these recordings. I can place more. Let's look at a tiny little snippet of code. I'm reading from the input a value n. I set k to be 1. And as long as k is smaller than n, I perform k equals 2 times k. And I'm asking what is the running time of this code as a function of n. That is, there is the running time, which is basically the only thing that happens here is how many times do I execute this loop, and I want to know it, what is this running time as a function of n. I mean, either give me an exact expression or tell me the answer both as big O and big omega. It's very simple equation, but and I bet that most of you already knows where it's going, but let's do it once formally. So since I'm going to use logs here, I'll mention to you a few rules about logs from, probably know it from the past. If you happen to have a blackout, you don't remember what is log, then if I look at every number x, then and I ask what is its log, then the answer is that log of x is a number such that 2 to the power of log to the base 2 of x, I'll write it larger for the camera setting. Here is x, and I'm trying to explain what is log to the base 2 of x. Then x is just 2 to the power of log to the base 2 of x. That is, if I take log of x and then I look at the exponent of what I get from the log, I'm getting x back. And similarly, x is also equals to 10 to the power of log, but now the log should be in the base of x of x. Okay, just to remind you what is this log function, how it relates to x, and this log have a few properties that here are the cheat sheet to remember them. Log of two numbers, no matter at which base it is, log of two numbers of a times b equals to log of a plus log of b, always true, no matter what the base of the log, but it needs to be the same base, the same number here of the three logs. Log of a to the power of b always equals b times log of a. That is, you're taking the b that is floating over here and you're placing it before the log. Taking the b that was here, putting it before the log. How can you move from base 10 to base 2, or between any two bases? Log to the base a of x is log to the base b of x, for example, base 2 and base 10, divided by some constant. What is this constant? Log to the base b of a. That tells you how to move from one base to the other, and what we'll care about over here is that if we'll write log to the base 2 or log to base 10, the difference between them is only a constant. And as I said, we don't care about constant, we don't give them any respect in this course. And finally, if x is smaller than y, then log 2 of x is also smaller than log 2 of y. And same for log 10. Back to our little code over here. I want to analyze its running time, and I want to say the running time, well, every time that I'm performing such an iteration, I'm spending some constant involved of evaluate this condition, still true or not true, and if it's still true, then I'll perform this operation, which in turn involves bringing things from the main memory, from registers, putting them in registers. However, it's constant number, constant, we also say it's order 1 time. Order 1 is just fancy way to say it's constant time per one iteration of this log. So how many times do I execute this log? How many times do I execute this loop? I'm sorry. And to do it systematically, let's ask what is the value of k, this number k, after the first time that I execute this loop. I performed k equal 2 to the k, so k that was 1, now it's 2, so k now is 2, and I'll write 2 as 2 to the power 1. Now I'll execute the loop once again. So after the second iteration, k equals 4, also known as 2 to the power 2. After the third iteration, k equals 2 to the power 3. Right? 2 times 4, 8 equals 2 to the time 3. And you can prove, if you want to be extra formal, you can prove it by induction, that after the ith iteration, no matter how many iterations you did, after each the ith iterations, k equals 2 to the power I. The same I, for every value of I. And now let's count the number, let's call this number j, the number of times that this condition that I evaluate over here is still true. Okay, how many times could it be that I evaluate this condition and this condition is still true? So if this condition is true, it means k is smaller than n. On the other hand, what is k? K is this number 2 to the j, the number of iterations that I performed so far. K is 2 to the j, and I need bound of j. How many iterations do I perform? So k, which as we said is 2 to the j, is still smaller than n, because I'm only counting the number of times that this condition is correct. How do I proceed? I take log to the base 2 of both sides. I take log to the base 2 of k, and I take log to the base 2 of n. Remember, I have 2 to the j is small or equal than n, and I perform log to the base 2 of this and log to the base 2 of this. Okay, and I'm using this condition. It also works in the other direction. If x is smaller than y, then log of x is smaller than log of y. So what happened to it when I take the log to the power 2 of k? What is k? K is 2 to the j. K is 2 to the j. So how do I write log of 2 to the j? What do I do with the exponent using this condition? What do I do with the b over here? Now j plays the role of this b, and I'll just move it to the beginning of the log. So instead of having the j over here, I will have j over here. So I'm getting that j log to the power of 2 of j, which is just j times log to the power of 2 of 2. I'm doing it once very slowly. You don't need to do it nearly as detailed as I'm doing it in the homework. Let's meditate on it. What is log to the power of 2 of 2? Log to the power of 2 of 2, which asks to which exponent should I write on 2 so I'll get 2 back, and the answer is 1. Log to the base 2 of the number 2 is just 1, just as log or to the base 10 of 10 is 1 as well, because 10 to the power of 1 gives you 10 back. So what should I do with the log to the base 2 of 2? This is just 1, so what I have on the left side is just j. And on the right side, I still have that it's smaller than log to the base 2 of n. So j, the number of iterations that I do, is order of log to the base 2 of n. And what is the overall running time? Well, the overall running time is just I made j iteration, and I just made j iteration. Notice that I'm exiting it when k is in the next iteration, because after when I evaluate the condition in the next iteration, k is larger than n, so I exit. So j is order of log to the base 2 of n, and remember we hate constant. We want to write as little as possible. How do I move from one base to the other? This formula. how do I move from one base to the other, say to base 10? I take log to the base 2 of something and multiply or divide by a constant. But big constant vanish inside the order, inside the big O, so I might as well just write its log without writing the base here. I don't need to write the 2 here. I can just write log to the base 2 of n, because the base doesn't matter, just affect the constant. And obviously this is also the lower bound, so the overall running time is order log n. Questions? Another example. For I'm reading n, for I is 1, I is smaller than n, I plus plus. For j equals 1, j smaller than n, j plus equal I. So j plus equal I, increment j by I, which is and I want to ask, and every such iteration I print an asterisk, just because if the question of what's a big O is confusing, I can just ask how many asterisks do I print, because printing an every time that the inner loop is executed, you're printing an asterisk, and that's the number, the running time is proportional to the number of asterisks. So what is the overall running time of this code as a function of n? First, one bound you can generate by saying this line, how many times it's executed, n times. How many times do I execute this value, this loop, the inner loop? Well, there is something fishy going on, but because I'm adding I to j, but I will be either 1 or something smaller than 1 or something larger than 1. So no matter what happens, it will not be more than n. But it will be at maximum n times that you'll execute this part for every value of I. So if this takes order n and this takes order n, then order n times order n is order of n squared. So a naive bound for this code is order of n squared. And now I want to show you that you can be a bit more accurate in this answer and say order of n squared is correct. It's true to say that it's order of n squared. My question next will be, is this a tight bound, or is the running time is actually smaller? Can you prove a smaller big O of n for the running time of this code? And the answer is that for this particular code, and I like it because it's a bit surprising, there is actually a different running time, a better bound. First, where are you saving something? Had I do in this inner loop j plus equal 1, add only 1 over here, then the running time is clearly n squared. No doubt about it, upper bound, lower bound. But you see, in some operation I add to j I, and I is becoming larger and larger. Everybody is familiar with this format. It just says right, j equals j plus I. So let's be a bit more sadder. And to answer whether it's omega of n squared, well, if I can prove better upper bound, then it cannot be order of n squared. It should be smaller as well. So to be a bit more sensitive, let's look at I and let's ask what will be all the values of j that I'm generating right here. And j will start as 1, as I, and as long as j is smaller than n, j equal j plus I, which is 1. So what will be the values of j? It will be 1, 2, 3, all the way up to n. Then I exit the loop, so I do it n times, and I print star asterisk for each one of them. Let's move to the case of I equal to. I equal to j start by being. I start when j is 2, and then I add to it 2, so it's become 4. I add to it 2, it becomes 6, 8, 10, and so on. Right? So j will run over all the even numbers between 1 and n. So in total, how many even numbers do you have between 1 and n? About n-half many such numbers. It could be +1, -1, floor, ceiling. We usually ignore in this course floor and ceiling. Very rarely I'll ask you to actually write what is a floor and ceiling. It's fine if you'll say you're not printing it more than n-half times and not worry about whether n is even or odd. So when I is equal to, that's the number of stars that you are printing. When I equals 3, I start when j equals 3, and at each iteration I'm adding 3 to I. So what will be the values of j? 3, 6, 9, 12, all the way up to n. So only the numbers whose modulo 3 equals 0, how many such numbers do you have between 1 and n? You are covering third of the numbers. So you're pointing n over 3 many stars. I equal 4 implies j will jump over 4, 8, 12, 16. So you're pointing quarter n many stars, dot, 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 until I equals n. And then you're pointing only one such number, n over n, just one time. And now I want to ask, how many stars did you print as a result of the whole loop, which is also proportional to the running time? And you'll need to sum up the case where I was 1, I was 2, I was 3, I was 1, I was 2, 3, 4, 5. So you need to sum up n plus n over 2 plus n over 3 plus n over 4 plus dot 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 n over n. All these numbers have n before that, so you're getting n times 1 plus half plus third plus quarter plus dot dot 1 over n. And this has a name, this sum has a name. So people that took calculus undoubtedly covered this part. It's called the harmonic sum. And this number is, the numbers that you see here in a parenthesis, is very close to be log to the base e, the natural log of n. Ln n. 1 plus dot 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 1 over n is ln n plus a little error. And all of it times n, so the running time of this code is actually n log n. N order of n log n, or n ln n to be precise. And it's a bit surprising because usually we see log n, we see when we have some kind of partition, dividing by 2, like divide and conquer, or binary search, or binary trees. And suddenly n ln n appears in a code that looks very different than partitions altogether, but because math is cool or uncool, you're getting that that's a running time. So quite surprising, I think. Okay. Pay attention to this example because many pieces of this course and many questions in the homework and the exam and etc. are all modifying, looking at a variant of this example. So look at this code. Read n. I set a constant a to be half. I'm not going to change this constant. And as long as n is smaller than 1, as long as n is larger than 1, I print n star. J goes to 1 till n. I print n stars. And now I modified n. I tell you the new n equals to the old n times half. That is, the new n is half of the previous n that you had a moment ago. There is a big inflation. I bought my house for $100,000, and then I lost half of its value. So the new N will be $50,000. I lost half of its value. Another bad years, I printed now $50, and I set the new N, that was what? Half A times the previous N, which is now 50, so it will be a half of N. So I lost half of its value, I'm left only with half of its value. And so on. So once again, my question is, how many stars do I print altogether in this whole loop? And please pay attention for this example. We are going to really recycle it many times. So first, why is this not an infinite loop? It's not an infinite loop because at some point A is smaller than 1. So at some point A will be, N will be some number, half of it, half of it, half of it. At some point it will be smaller than 1, for sure. Each time that you multiply by half, you decrease it. I'm not asking you how many times the whole loop is executed. I'm asking how many stars are there executed. But had I asked you how many times do I call the inner loop? How many times do I call the inner loop? Help? Not how many stars, not how many times not how many times I execute the print, how many times do I call the for? And somebody says, can you speak up?
Would it be log base A of N?
It would be log base of N, absolutely. Exactly the same exercise that we saw a slide or two ago. But now I want to actually ask, how many stars do I print? And the answer will be, let's be more gentle and realize that every iteration there are fewer stars, fewer asterisks. So what happened at the first iteration? I print N asterisks. So the running time will be an order of N. What happened in the second iteration? I'm using different N. It's the original N that I set as an input, multiplied by A, making it A times N many stars. If A is half, then it's half N many asterisks that you print. What happened in the third iteration? What is a new N that I'm using right now? It's A times the previous N, which was AN already. So it's A squared times N. A times N. Half of N many stars are printed in the third iteration. What happened in the kth iteration, k equal 4, 5, 6, etc. I'm printing A times k many times times N. Each time it lost 50% of its value, so I'm left only with half times N. How many times half? Well, depending on how many, what is K. It's A to the power of K times N. That's how many stars you're printing in the kth iteration. And now I'm asking how many asterisks did you print all together? And once again, let's sum up all these numbers. What do we get? We are getting N plus, that was from the first iteration, plus A times N, that was when from my second iteration. Third iteration, A times N, quarter N, many asterisks. Third iteration, A cube, A to the power 3 times N, etc. all the way until the last iteration that, well, we know that it's log based of 2 of N, but we don't, as you'll see in a second, we don't care. In the last iteration, I'm printing A to the power of T is the last iteration, times N many stars. All these terms over here have N inside them, so let's gather all of them, put n outside of the parentheses, and telling the number of stars would be n times 1 plus a half, for example, a square quarter, for example. In the case of a equal half, then the sum looks like n times 1 plus half plus 1 over 4 plus 1 over 8 plus dot dot dot. And then I need to write something as a last expression, but instead I tell you, you know what, we are all lazy, at least I am, honestly, and instead I'm going to add a few little elements over here at the end, but I don't care because they are so tiny. Then actually I let this sum keeps on going all the way to infinity. I'm just adding elements. So this sum that I need to end up at n to the t is smaller than n times 1 plus half plus 1 over 4 plus, and go all the way to infinity. Why do I want to go to infinity? Because it makes my life simpler. It means that I need to write less and I have fewer chance to make mistakes and typos. So I'm getting n times 1 plus a is half, all the way up to a to this t, which is in turn smaller than, look at all the elements all the way up to a to the t and add a to the t plus 1, a to the t plus 2, a to the t plus 3. You'll continue with it for infinity, and now you're saying, oh, I know what you are written right here in the parentheses. What did you write right here in the parentheses? What is this value of 1 plus half plus quarter plus all the plus 1 over 8, etc.? You know, or if not, take my words, it is just 2. That's what I'm getting. If I'm going all the way to infinity, this sum will converge to exactly 2. And in general, for any geometric sum looks like 1 plus a to square plus all the way up to a to the t. It's obeying this formula, 1 minus a to the t plus 1 divided by 1 minus a. And if I'm taking a to be smaller than 1 and going all the way to infinity, I'm getting this simpler expression because a to the t plus 1 becoming 0, so it's just 1 over 1 minus a. So what do I get over here? N times 1 over 1 minus a. I think that it's cool, no? It's all what you're presenting is what you'll get over here in this expression will be n times 2, linear in n. It's a bit surprising, I think, because if you look at the first iteration, when I used the original n, I still used n stars. And if I look at all the iterations all over the place, I still use only order of n. It's still linear, just different of a constant. Right? It's n times 1 divided by 1 over a. Why is this result so crucial for us? Quick application is coming, for example, from computer graphics. You have a model that of your beautiful coffee cup, and you have your coffee cup and you draw it with many triangles, lots and lots of details, and you're saying, if I need to render it in my, I'm building a computer games, if I need to generate it with all the triangles, all its details, then I'm using all the I'll use the full model, and it has n many triangles, and let's say n is a few million or billion of triangles, very detailed. But I'll also keep another copy that have only half many triangles, which I will use if the copy is further away from you. You don't need such a high resolution, so you'll use a model that has only half many triangles. And if the copy is even further away, you'll use a model that have only quarter many triangles, only 1A triangles. So this is called level of details in computer graphics. You'll keep the same model, the same data multiple times, but with different resolution. And how much memory do you spend altogether? Well, I keep the cap multiple times, log n times, but still the overall penalty that I'm using is at most 2, and actually it's more commonly it's you're reducing it a bit further, so you only have an overhead of between 100 to 30% by keeping multiple levels, which practically is nothing. And the big advantage is that you can choose online, depending on your computer game, where is a player, where is a viewer, and where is a cap, which of the copies you are going to use when you're rendering it, because there is no point to render a very detailed cap if the cap is far away and you're below the pixel resolution. That would be one of the many applications of this little result. So did everybody understand everything that I said so far? You got 80% of your final grade if you really fully inhaled this result and completely understand it, because it will repeat multiple times. Moving along. More about theta. I already said it, that omega, sometimes we are talking about omega of algorithm. This is a slow algorithm that runs in order n square, that runs in omega of n square. For example, insertion sort runs in omega of n square, but maybe other algorithms runs much faster. Or you can speak about omega with respect to the problem, sorting at all. No algorithm runs in better than omega of n in general. A problem like TSP, traveling salesperson, you assume that the running time is at least exponential unless p equals np. Another type of such behaviors that you can all talk about, that unless everybody is wrong, no algorithm in the world running in better than n log n, so no point of looking for such an algorithm, and so on. And we are done with our introduction to the course. Once again, the cs445 salute, the gesture of disqualify. And let's start with our first topic, which is the stable marriage algorithm. Everybody please wake up, starts to be pretty cool material. I always put it at the beginning because it has lots of fundamental ideas. It gets everybody's smiling, and it shows you that theory and algorithms could be very cool. And you'll find CLRS, the textbook CLRS does not cover it, as the other textbooks that I recommended by Eva Tardosh and Dan. The other textbook does contain it, and of course the slides themselves and wiki is not too bad as well. Okay, we are going to talk about the dating in 1950s, where rules were quite asymmetric, and we are going to tell you how to obtain stable marriage. Of course, there is how to obtain stable marriage. And we are going to discuss in particular the very famous Gale-Shapley algorithm for the stable marriage, stable matching algorithm, originally published in a paper in 1962 by Gale and Shapley, named Colored Admission and Stability of Marriages, appeared in the Mathematical Monthly, and it's explains stability actually in economical markets, in addition to what type of stability, somehow related to Nash equilibrium, and what guarantees some type of stability in the market, as well as how to assign resource to location, like I have post offices and people, and I want to assign to every person to an office in a way that that no public office will be overcrowded, but still the assignment of people to post offices will be legit. And it was a base of lots and lot of research about resource allocation, about different types of matching altogether. There is a fantastic book by Dust Goldfield and Irving, that's a big book that will tell about, is that called the stable matching problem. A lot of results about it. Lots of setting, lots of application. As I said, by the way, if you just look for Amazon for books about stable marriage, that probably will not be your first hit. But if you look for stable marriage and problems, that probably will not be the first hit. If you mention algorithms, maybe it will be. There many other books about stability in marriage of algorithms. And just a bit self-promotion, one of the other papers that appeared later on talked about geometric stable roommates, not married in some geometric setting. It was contribution of myself and colleagues. And I want to tell you back what is a classical stable marriage algorithm. I'll describe it in the way that appeared in most textbook. It is, and I'll use the same terminology. It by no means express my opinion or what is fair or what should be done. It's just the tradition of the slides or the textbooks that describe it in the following way. So here is our problem back in the abstract way. The input consists of n males and n females, and each person must rank the opposite sex. In this problem, we'll assume we'll generate marriages or generate couples that consist of one male, one female. Again, no hint about what is correct or appropriate. Just in this algorithm, that's the type of matchings that we are handling. And we'll assume that their numbers is the same, n males and females. And what the input of each male is a full ranking, or the input of each participant is a full ranking of everybody of the opposite sex. Every male should have a full ranking, full meaning each one should be ranked. And male 1 says my preference list is female 3. She will be the first, my top choice. She's the one that I really want to marry. If she's not available or interested, I want to marry female 2. If she's not interested, I want to marry female 5, all the way until the last female. And male 2 will give also a preference list that might be identical to male 1, might be very different than male 1. No constraints about how similar or different the list should be. And similarly, female 1 will say male 3 is the one I really want to marry. If he's not available, I'll settle for male 5. He's my second choice. Male 2 is my third choice, and so on. That's the input. And so the input of the algorithm are all these lists. Remember, the input is already consists of n square much memory, the total list of all the list from each one of the participants. What do we want as the output is so a one-to-one matching. Tell me to each male which female he is married to and vice versa. And each male will marry only one female, each female will marry only one male, and this matching should be good in some sense, should be stable. And by the way, the classical application of this problem, or some other classical application, is a famous problem of residence that residents that finish med school needs to go for residency. They rank the hospitals that might want them. Every hospital in the state rank all the candidates, or the top 20 candidates, or whatever. And now we look for matching of residents to candidates in a way that accommodates both hospital and residents' wishes, and try to optimize one of a few parameters. That's yet another classical application of the stable marriage algorithm of residents and high school. Or I believe that in New York, that's actually how a high school pick students based on similar list of preferences. Yeah. The books that I mentioned before, you have the details on the slides if you want to look for it more. Just to make formally a matching here, when I'm discussing a matching, I mean a list of n pairs. Tell you my list of n pairs. Each pair consists of one male, say male 1, one female, female 13, and every pair consists one, and no males appears in two such pairing, no female appears in two such pairing. Usually, it's not the only case in this course that we are talking about bipartite graphs. We'll see other matching algorithms, but usually we'll think about it as male 1, male 2, male 3, female 1, female 2, female 3, and you'll think about a matching as a, but intuitively you'll think as a one-to-one matchings, namely, for example, male 1 will 3, male 2 will be married female 2, male 3 will be female 3. And this will be one possible matching. That is, a matching will not be just a pair, it should contain the list of all the pairs. That's what the algorithm needs to spit out. Quick question, how many, if I have n males and n females, how many matchings can I have? Ignoring the preference, just n males and females, all different. How many pairings do you have? I think that more than n. N is the size of the married, but here is one such matching. Here is in blue another matchings. In green I will produce another matchings, and so on. Each such matching. So what was your answer? The second answer?
Well, then I said
Sorry?
which one of them?
It's not n to the n, because why it looks like n to the n, let's say female 1 decided about somebody, then female 2 needs to decide about somebody, but it cannot be the one that already taken by female 1, so female 2 has only n minus 1 choices. Female 3 has only n minus 2 choices, and so on. So altogether, the number of matchings could be n times the number of choices of the first one that picks, times n minus 1, times n minus 2, times dot 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 all the way until the last person that picks that has only one choice, which makes indeed n factorial. Remember it and remember how we got to this number. So that's what we want. Okay. So, and just to explain what is exactly this preference list or preference list, we'll think that each person gave a preference list, an array, a file, at which there are a sequence of n numbers, and I just repeat what I said. The first number means if the first number is 5, means the pick choice of female I is male 5. If he is not available, the second number is the second pick, and so on until the very last bottom, the last one. But each one of the males must be there. And now we have 3 minutes, which is just enough to tell you what is a rogue couple, rogue unstable couple. So I cannot say what is I cannot look at two people and say they are a rogue couple. I need to first assume that I have some matching. Somebody gave me an assignment of every male to each female he is married to, then vice versa. And I'm looking now at two people, let's say Zod and let's say Aradia. And I want to ask, are they a rogue couple under this marriage matching M, this arrangement? So I first say Zod and Aradia, if they are married to each other, they are not rogue. They are very stable in this sense. I don't know that they are unstable. I'll say that Zod and Aradia are unstable only if a few conditions should satisfy. To start with, Zod should not be married to Aradia and vice versa. We need to marry to other persons. To define rogue couple, I'm looking at male and female not married to each other, but now I look at their preference list and I look to whom they are married. And in this case, in my example, Zod is married to a Vanora, which is number 6 on his list, meaning Corodia, Cascadia, Arabia, all of them. He would prefer Allegra over number 6, Avanora, which is his wife, and meaning heirs. In particular, Aradia is higher on his list than his wife. But that by itself doesn't make it unstable pair yet. But now I look at the preference list of Aradia as well. And in her preference list, she is married, I'll describe here, to Syndrome, that's her husband. However, on her list, Zod appears higher than Syndrome. She would prefer to marry Zod over married Syndrome. In other words, and then they start talking to each other, and they realize that both of them prefer each other over their spouses. Zod prefers Aradia over his wife, Venora. Aradia prefers Zod over her husband, who is Syndrome. Why is there an instability in the system? Because if they'll dump their mate and marry each other, both of them will upgrade. Both of them will marry somebody that they prefer more comparing to their current spouses. So they both have an incentive to change the system, to change this marriage. They are a rogue couple. Okay. We made something wrong in creating the matching to everybody because this couple will be unstable. Of course, I have many other reasons why not to break it, and I don't talk about moral reasons here. I'm just defining what is unstable pair. Unstable pair would be a pair under matching, would be a pair not matched to each other, but both of them prefers each other over their current spouses. They defined a rogue couple. And how can we get a matching that doesn't have a rogue couple? Well, we'll say if Zod would prefer Aradia, Aradia will say maybe, hey Zod, maybe you're not my top choice, but at least I will just downgrade if I'll marry you because I'll prefer my husband over you, or vice versa. If one prefers the other says, my husband or my spouse is already better than you, so I don't have any incentive to break the marriage and marry you. If I have a marriage at which there is no rogue couple, that's what we call a matching is called stable if it does not have any rogue couple. And it's very easy to get confused. To get what are the potential rogue couples, these ones are the couples that are not married to each other. Couples that is married to each other cannot be rogue. Couples that are not married to each other, we have n square, many pairs not married to each other, they potentially rogue depending on whom are they married to and what are their preferences. So what we will study is how to find a marriage at which there are no rogue couples, at which there is stability in this sense. And in the economical world, if you think about it, you will have some stability in the market if every time there somebody change somebody, he will gain, but the other side will lose. That will be, it at least suggests some stability, and that's where it's touching economy out there, and that's why they got a Nobel Prize for this and other observations. Okay, so we'll study how to find it, and it will be very cool and very entertaining. Promise. See you Tuesday. Thank you. Questions? Anything?
Thank you.